Uno, dos, tres, cuatro.
Hi everyone, welcome to Trig 2, the beginning of our next unit in Pre-Calc 12. We just finished Trig 1 and now we're going to take a look at some proofs and see how everything can all be put together. So before we get started, you want to make sure that you have an identity sheet. So if you're in my class and you print out the last page of the package, you'll notice that there's a bunch of formulas, and you're going to want to have those formulas handy, and it's something that you'll have access to for all future assessments, quizzes, tests, exams, anything that you need it for, you'll be able to refer back to it, and it's going to be very, very useful for this unit. So let's take a look at exactly what we're going to be doing and what do we already know about trig identities. So there's some identities that we've learned from Pre-Calc 11 and a whole bunch that we've learned from the first unit in trig for Pre-Calc 12. And if we take a look at something called the reciprocal identities, there's three of them. There's cosecant, secant, and cotangent. And we're saying that we know that cosecant is equal to 1 over sine, secant is equal to 1 over cosine, and cotan is equal to 1 over tan. And those are three things that we're going to be using over and over today. There's two additional identities. We've learned in the past that tan is equal to sine over cosine, and what we can conclude then is that cotan, which is the reciprocal of tan, will be equal to cosine over sine. So those five different identities are five identities that we're going to be using for some of our examples here. The next identity that we're going to look at, though, is something called the Pythagorean identity. And the Pythagorean identity goes like this. We've drawn a unit circle a bunch of times before, and we know that when we want to draw a unit circle, you construct a right-angled triangle where the hypotenuse is representing the radius. And when we have a unit circle, we know that the radius is represented as being 1 unit. If the point that we're trying to find is an unknown and we call it x comma y, you'll know from trig 1 that x was equivalent to the cosine value and that y was equivalent to the sine value. So while we say that the point is xy, we also know that we could call the point cosine comma sine. And based off of what we can label then, we know that our horizontal value right here is going to be cosine of theta, because that's the x value that we've traveled over, and sine theta because that's the y value that we've traveled up. And if you wanted to make some sort of statement based off this using our famous a squared plus b squared equals c squared, we could now say that sine squared theta plus cos squared theta will equal 1 squared, or we could just say 1. Now, note that when we say sine squared theta, saying something like sine squared theta is equivalent to saying sine of theta being squared, and it's just that the notation that we write it in looks more like having the squared first instead of the bracket and then the squared on the outside. So on your formula sheet, you'll see that sine squared theta plus cos squared theta equals 1 will be one of your additional identities that we're going to use for some of our questions for today. And underneath that, I just want to list one other thing that you could also say, actually two other things. Each of these can be manipulated to create more identities based on what you might be looking for. So if we know that sine squared theta plus cos squared theta equals 1, we could also isolate for either sine or cosine to create two different versions of this identity. What I mean by that is we could say that sine squared theta is going to be equal to 1 minus cos squared theta, and cos squared theta is going to be equal to 1 minus sine squared theta. And keep those in the back of your head because we're going to be using some examples where you might be able to directly replace that and make it a little bit easier when we do some of these identities coming up. There's a couple other identities that you'll notice on your formula sheet. So here's one and here's one. When I was in high school and I saw those two additional identities, I just took it for granted and I didn't really figure out why it's the case that these are true. So I'm going to say two things about them. The first thing is this: we can also manipulate them. So if we want to manipulate them, we should be really clear that, and you want to write this in here, that you could also say that that means that tan squared theta is equal to secant squared theta minus 1. And for the one on the right that we have right here, we could isolate for cotan squared theta, and we could say that that's cosecant squared theta minus 1. So if the first thing that we want to talk about here is that they could be manipulated, the second thing we want to do is we want to understand why they are trig identities, and specifically why are they a Pythagorean identity. So this is more theory than anything else. If you take a look at tan squared theta plus 1 equals sine squared or secant squared theta in the middle here, let's rewrite this in terms of sines and cosines so you can see how similar it is to our identity on the left. Tan squared theta, as we saw from above, is equivalent to saying sine squared theta over cos squared theta. So we can say sine squared theta over cos squared theta plus 1 is equal to, and instead of saying secant squared theta, what if we say that's 1 over cosine squared theta? So if we have something like this, and you were doing some sort of balancing, and we wanted to get rid of the denominator by timesing both sides by cos squared theta, look at what happens. Here we go, times by cos squared theta, times by cos squared theta, and times by cos squared theta. If we do that, then our cos squared thetas cancel out here and here, and we'd be left with a statement that would say sine squared theta plus cos squared theta is equal to 1. And we know that's true because of our previous Pythagorean identity. So because of that, we know that tan squared theta plus 1 equals secant squared theta. Okay, finally, if we want to do the exact same thing with our 1 plus cotan squared theta equals cosecant squared theta, we could do that by saying 1 plus cos squared theta over sine squared theta equals 1 over sine squared theta, and then we could times each of the numerators by sine squared theta to eliminate the denominators. And if we do that, the sine squareds would cancel out, and we'd be left with sine squared theta plus cos squared theta equals 1. So we know we've done that correct as well. Okay, now what does all of this mean? If you're thinking about this trig 2 versus trig 1, you'll notice that everything's going to be a little bit more algebraic and a little bit more theoretical. We're going to learn how to do proofs. We're going to learn how to balance and simplify complicated trig expressions and something called trig identities. So if we take a look at our first example now, it wants us to say if secant squared x minus 1 times cotan squared x is the expression that we have right here, can we simplify this into making it something that's going to look a little bit cleaner than what it currently is? And when it's not a multiple choice question and it's a little more open-ended like we have with these examples here, sometimes that can get a little bit frustrating because we're not sure exactly where we're headed with this, and we might not always be sure exactly when we're done. But you'll notice that we can actually clean these up quite a bit, and hopefully you'll get used to them quite quickly. Look at secant squared x minus 1, knowing that x is the same as saying a theta, and compare that to some of the Pythagorean identities that you had from above right here. And if you take a look at that, we saw that secant squared x minus 1 is equivalent to tan squared x. We had that right here. And so if that's the case, we can replace that bracket by saying this is equivalent to saying tan squared x. And if you have cotan squared x, you could write that as something as well. So look at what cotan x is equivalent to from your identities at the top. And one of the things that it's equivalent to is, instead of saying cotan x, you could write it as 1 over tan x. And if you wrote that as 1 over tan x, except in this case we're going to say 1 over tan squared x because we're dealing with squared values, then the tan squared x here and the tan squared x here are just like variables that you would have, like an a or a b, and you can reduce them and you're just left with nothing but 1. And so that may have looked a little bit easier than what you would have guessed, but there's other ways to end up with that same end result, but that's the most efficient way to be able to get there for that question. So what we're saying is that statement right there, that expression, is equivalent to being simplified to the number 1. Okay, let's continue on with example B and let's see what we could say with that. So first thing is, let's look at 1 minus sine squared x and let's see how we could replace that with something else. So if you take a look back up to your Pythagorean identities and we saw that 1 minus sine squared x is equal to cos squared x, then we could say that 2 cosine x, that's just rewriting the numerator, over cos squared x. And we want to figure out how we can reduce this. So cosine x is just like any other variable. And imagine you had a variable that said you had 2a over a squared. How would you reduce that? Well, you would say one of the a's on the top can reduce with one of the a's on the bottom. The same thing would be true here, where one of the cosine x's can reduce with one of the cosine x's. And you'd be left with 2 over cosine x. And so for something like that, I would say that's a correct answer and you can leave it like that. And the other thing that we should talk about though is sometimes you might not, if you can not leave it as a fraction, that could be even better. So having 2 over cos x is good, but you could also say, I know that 1 over cosine of x is equal to secant x. And if that's the case, then instead of writing 2 over cos x, I could write 2 secant x, and that would be the equivalent statement. So both of these are good, and if you're to look up the back of Michelson, I'm going to guess that he probably went with the latter. He probably has this because it looks a little bit cleaner than just saying 2 over cosine x. Okay, so let's look at a couple more examples that we have right here now. How would you simplify something like 2a? Whenever you have multiple fractions, probably one of the best things you want to do is be able to say, well, hey, can we join this into a single fraction? That's my best way of being able to simplify something. And if you look at that, you want to find some sort of common denominator. And you'll remember back from when we did so much of this in pre-calc 11, your common denominator of something like this would have to include both factors. So you'd have to say my lowest common denominator is going to be 1 plus cos x times 1 minus cos x. And then you would times this by 1 minus cos x, and whatever you times to the bottom, you times to the top. So we're going to have to times the top by 1 minus cos x. And then for 1 minus cos x on the bottom right, we're going to times that by 1 plus cos x. And then up here, we're going to times this by 1 plus cos x. So what that does is it gives us a common denominator, and it gives us a common denominator of 1 plus cos x times 1 minus cos x. And on the top, we have sine x being times by 1 minus cos x, and then sine x being times by 1 plus cos x. So if we distribute that there, and we take the sine x here, and we distribute it through, you would get sine x minus sine x cos x. So that's just saying sine x times 1 becomes sine x times cos x is sine x cos x, plus sine x plus sine x cos x. Okay, and that's just distributing the second values. Okay, so if we want to continue to simplify this, on the top, we could look at this and you could say, well, do I have some like terms? And here you have a positive sine x cos x, here you have a negative sine x cos x, and if you added them together, because they're like terms, you're allowed to do that. They would cancel each other out because they're the opposite signs of each other. And you'd be left with 2 sine x on top. 1 sine x plus 1 sine x adds up to 2 sine x's. Just in the same way that you can add any like terms, sine x's are like terms. You have one of each of them, so together you would have 2 of them. Now on the bottom, you might say, I'm stuck here. I don't really know what I could do. And once we've gone through a few examples, you'll get to notice some trends of things that happen. If we're to expand this bottom here, and if you're to try to see how that could potentially simplify, you know that you have a difference of squares, and you would get something that would say 1 times, and then 1 times negative cos, which is negative cos, and then plus a positive cos. The two middle terms are going to cancel each other out. They're the opposites of each other, and then you'd be left with cos x times negative cos x, which would be negative cos squared x. And that actually really helps us out. When you look back to your Pythagorean identities, so go back to the previous page and look at the different Pythagorean identities options, and you had something there in which sine squared x is equal to 1 minus cos squared x. So this denominator here is equivalent to saying it's sine squared x. So what we could do is we could rewrite this, and we could say we have 2 sine x over sine squared x. And then based off of that, we can now reduce it. So the sine x on top reduces with one of the sine x's on the bottom, and you'd be left with 2 over sine x. That's a good answer. And then think about what Michelson might have in the back of the book. If instead of having it as a fraction, you wouldn't have to express it as a fraction. We know the reciprocal of sine x. So something equivalent to 1 over sine x is cosecant x. So we could say we have 2 cosecant x, and that would be an equivalent statement for something like that. And we can leave it like that. Okay, so I would pause the video right now, and I would take a look at part B and see if it's something where you think you might be able to do a little bit more of part B on your own now. Let's find a lowest common denominator. It would be cos x times 1 minus sine x. And we'll times the bottom left by 1 minus sine x, so we times the top by 1 minus sine x. We times the bottom right by cos x, so we times this by cos x. Based off of that, we get a common denominator, and our common denominator is going to say cos x 1 minus sine x. And then on the top, we want to see what we could do to expand and simplify that. So if you have 1 minus sine x and you're timesing that by 1 plus sine x, maybe I'll just write that out for the first time just so we can see that a little bit better. And then that's going to be subtracted by cos x times cos x. So we could say cos squared x. Okay, so in the same way that a times a is a squared, cos x times cos x is going to be cos squared x. If we FOIL this top here and we say 1 times 1 and so on, we would get 1, it's a difference of squares, plus a sine x minus a sine x, so those will cancel out, minus sine squared x minus cos squared x over cos x 1 minus sine x. And now this does look a little bit awkward. The top isn't super straightforward, and you might have this aha moment. If you take a look at the 1 minus sine squared x, and you think back to what that could be equivalent to by looking at your Pythagorean identities, you would see that 1 minus sine squared x is equivalent to cos squared x. Okay, so look back up there and look at what you had when you had cos squared x isolated, and that is equivalent to saying cos squared x. So we could now say we have cos squared x minus cos squared x over cos x 1 minus sine x. You might be saying, do I need to expand the denominator? You could, but I don't think it's going to be helpful. And you'll notice in this question especially, it's not helpful at all. You can now join like terms on the top, and you have a cos squared x minus a cos squared x, and those are like terms. And if you have the same thing, 1 cos squared x minus 1 cos squared x, that's going to equal 0. And 0 divided by whatever that denominator is going to stay 0. So believe it or not, that expression simplifies to just be 0. Okay, let's look at a couple more of these examples. You might start to think that, wow, okay, I'm in for something with this unit. There's some tricky questions here. Next class, we're going to formalize all of the different rules, and we're going to put them in an order so that when you check through these rules in a certain order, it's going to allow you to be able to make the best decisions to be able to come up with something that's going to balance out or simplify in its best way. When we go through those rules, the first rule, and this is the first rule that we have with a lot of our math, is we want to factor first. So if you have something in which you're going to be able to say, can I factor something out of the numerator or can I factor something out of the denominator, that's usually going to be able to help you out with something. And that comes into play with example 3a here, where if you look at the numerator, we can factor out a sine x. And we'd be left with cos x plus 1. And on the denominator, we could factor out a cos x as well, and we'd be left with 1 plus cos x. Cos x plus 1 is exactly the same. It's equivalent to 1 plus cos x. And because of that, we can cancel those out, and we're left with just sine x over cos x. Is there a way that you could simplify that so you don't have to worry about a fraction? If you look back to your original identities from the beginning of this lesson, we know that sine x over cos x is equivalent to tan x. So our best answer for something like this will be to say it's equivalent to tan x. Once again, I would pause and I would take a look at example B just to see if you'd be able to come up with a simplified solution for that. Let's factor first, and let's take out a cos x. So if we take out a cos x right here, we'd be left with cotan x plus 1. And on the bottom here, we could take out a cotan x, and we'd be left with 1 plus cotan x. Just like the last question, those bracketed values are equivalent to each other, so we're able to reduce those, and we're left with cos x over cotan x. So cos x over cotan x is a little bit more complicated to simplify. We'd say this would be saying cos x divided by, let's change cotan x so that it's something in terms of sines and cosines, because that might help us reduce it with something that has that cosine on top already. So look back and we know that cotan x is equivalent to saying cosine x over sine x. And when you're dividing fractions, you know that you multiply by the reciprocal. So that would be equivalent of saying cosine x times by sine x over cos x. So we took the reciprocal of our denominator. And because of that, we can reduce those cos x's now. And we'd be left with just a sine x. Okay, this final example actually is a little bit different from most of the questions that we have here. It's just saying, what are the restrictions for tan x and cosecant plus cosecant x? And it actually is more of a trig 1 question than it is a trig 2 question. So if you take a look at something like this, we want to say, can we write tan and cosecant in terms, maybe another term, to be able to see where we could potentially have 0 as a denominator. So for tan x, you could rewrite that as saying sine x over cos x. And I know you might be saying, well, couldn't I have also written it as 1 over cotan x? And you could have, but we know in terms of finding restrictions, probably having things in terms of sines and cosines are going to be a little bit easier than having them in terms of tans and cotans. And instead of writing cosecant x, we could write this as saying 1 over sine x. So what do we mean by restrictions? Well, we know your non-permissible values would be saying that cosine of x can't be equal to 0. If it was equal to 0, that would be one of the restrictions. You'd be dividing by 0. And we also know that sine x can't equal 0 because that would also be one of your restrictions. So between 0 and 2 pi, when is cosine of x equal to 0 and when is sine x equal to 0? And there's multiple ways to do this. You could draw your unit circle around here. For today, what I'm going to recommend is this. We're fresh from graphing sine and cosine, and we've done so many mini graphs to just get the rough idea of what sine and cosine look like. Let's take a look at that. If you have cosine right here and you did a mini graph, being that's 0 to 2 pi, where is it equal to 0? Where is it on the x-axis, which is right here and here? And that's occurring at the first quarter point, which is pi over 2, and it's also occurring right here at 3 pi over 2. So cosine of x is equal to 0 at pi over 2 and 3 pi over 2, and those are going to be two of your restrictions. If you're to do a mini graph of sine, that would be occurring at these spots right here, and that would be at 0, pi, and 2 pi. Notice that the restrictions that they're asking for fall between 0 and 2 pi, but not inclusive of 2 pi, because that's when you're starting your next period. So we don't have to worry about stating that 2 pi right there because that's a repeat, but we do have to say that we would have something on the x-axis at 0 and at pi, and those would be our additional two answers. So there's 4 values that are undefined, 4 restrictions, and that's happening at pi over 2, 3 pi over 2, 0, and pi. Okay, that's a pretty of a heavy lesson to start off Trig 2, and here's the homework. If you have any questions, make sure you ask me in class, make sure you come to tutorial, but that's the lesson for today. Thanks for joining.